Okay, in case you missed the notes from class today, this can be written in your math notebook or straight on the worksheet printing from the attachment. So what would it look like if you're doing it in your math notebook? You're just going to write down what's minimally required. Please title it the number of the assignment on Google Classroom, notes, day 1, and then 8/18 is today's date or whatever date you do the notes. And then we're going to write these notes together. I'm going to write on the worksheet in case some of you printed the worksheet, or you can write it in your math notebook. That's perfect. So first question says describe and label the pattern of change. So this is a review of Math 1 where we're going back to just starting straight from a pattern. So at the beginning means time 0, and then 0, 1 minute, 2 minutes. That would be if we were making a table, your X value. Then we're saying how many dots were in each of these scenarios. At the beginning or time 0, there's 1 dot. At time 1, there's 1, 2, 3, 4, 5. We're starting to notice a jump between the two. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's the jump from 1 to 5 and 5 to 9? We'll notice it's an increase of 4 each time. That plus 4 is called something. Back in Math 1, we had some vocab words for this. It was called the common difference. It was called the rate of change. We know that linear and arithmetic sequences had constant rates of change. It was adding by the same number every time. And also we just sometimes call it the good old slope. Describe and label the pattern. We could say that this is adding for each time to the previous term. We could also describe that the sequence begins with 1 dot at time 0. So if you remember back to how your Math 1 teacher taught you to describe these patterns, you're thinking of all the ways you could write these things in your own words. Assuming the sequence continues in the same way, how many dots are there at 5 minutes? First of all, there's the table guide. Up here would be the time, like time 0, time 1, times 2. And down here, there's dots. So the table guy, or girl, might say at time 0 there was 1. At time 1 there was 5 dots. At time 2 there were 9 dots. And then they might continue that table out to 5. So adding 4 each time, adding 4 each time, adding 4 each time, we say there's 21 dots. But what if Ms. Sanchez asked you for 100 minutes? We learned that there's a more efficient way to calculate this in case we don't want to make a table or graph something. So we learned how to write recursive and explicit formulas last year in Math 1. And this year we're still going to write recursive and explicit formulas. And the most useful formula, the explicit, we're going to graph from it. We're going to evaluate plugging things in and getting outputs from it, etc. So how do we write that recursive? Do you guys remember this format? Begins at time 0, there was 1 dot. So we'd say f of 0 equals 1. F of n equals f of n minus 1 plus 4 every time. So there's my recursive. My explicit formula begins with 1, adding 4 every time to the 1 before times 0. So again, n minus 0, some of you may have just written this as 1 plus 4n, and that's totally acceptable. Some of you may have even written it as 4n plus 1, and that is totally acceptable. This page, all we did was those notes, and now we're going to switch to the back page. We did the exercise together in class on practicing more recursive and explicit. So again, I'm now on page 2, or you're writing this in your math notebook. Pause the video and copy down these sequences. Write recursive, write explicit, and we're going to find those on all 3. See how you do, and then unpause the video and come back and check yourself. Remember that when it's just a sequence, what assumed number is above it in the table would just be starting at time 1. So count these all as time 1 sequences. All right, let's see how you did. So if this sequence was going constantly at adding 6, like we're noticing, 37 would be our next consecutive, and then 43 would be this one. So here I go. F of 1 equals 13, starting at 113. F of n equals f of n minus 1 plus 6 every time. In fact, you guys are starting to remember that that recursive starts with the same thing every single time. Whether it's letter n, letter x, letter t, f of n equals f of n minus 1, f of n equals f of n minus 1, f of n equals f of n minus 1, that always stays the same. What does change is that first term. This one's f of 1 equals 43. This one's f of 1 equals negative 1. So the only slight change there is we need to know what that first term is. So let's go over here and see how this pattern is continuing. This one is going down instead of up. So we're going from 43 down to 38, 38 down to 33, 33 down to 28. Please feel free to grab a calculator and double check yourself, but going down by 5 it should be. So that makes us to a 23, that makes us to an 18 here. The sequence continues. So this one's f of 1 equals 43, f of n equals f of n minus 1, and this time we're subtracting 5 every time to the one before. Last, what is this sequence doing? If you look at the negatives and it feels confusing, just look at the positives. From 0 to 1/2, what's that increase? It's just adding 1/2 every time. 1/2 plus 1, half is 1, and then plus another half. You could write it as 3 halves or as 1 and 1/2, and both would be correct. So we're just adding 1/2, and that's it. So our recursives look great. Those are nice and easy to remember, but those are not the special, useful functions. We really need to know the explicit function. It's useful. Given an input, I can get an output. I can graph it. It's much more useful. So how do I get those explicits? Well, they all start with the same function name as that recursive. They're all going to be f of n equals in this case. But this time, we have a form that goes, begins with what? Adding what? Every time to the what? Just kidding, n minus 1. Where does this 1 come from? It's because this is the time 1 function, right? Where does this come from? This plus 6 is because we're adding 6 for our common difference every time. And finally, where does this 13 come from? It's because we began with 13 up there. So look where all those pieces come from, and then look where they showed up in that recursive. All those same numbers showed up in the recursive in these respective spots. Pause the video and try those explicits if you didn't get them before. All right, let's see how you did. Begins with what? This time, subtracting what? Every time to the n minus time 1. And finally, begins with what? Really? I could start with a negative? Yep. Adding what? Every time to the one before time 1, n minus 1. How'd you do on those? Excellent.